Okay, lecture 13, the reaction quotient. QC is very much like KC, except KC is only when you see KC, that means you're at equilibrium. QC means not necessarily. I'm going to write all the caps. Not necessarily at equilibrium. Not necessarily at equilibrium. It can be, just by chance, but mostly when you see you're using QC, it means that you're somewhere in the middle of the reaction. And so the reaction has a ways to go. It either is going to keep shifting to the products or back to the reactants, one or the other. So the QC allows us to determine which way the reaction is going to go. And that's the thing, is this is a reversible reaction. Even though we've written it as in this form, we could certainly just put in the, this is phosphine. We could just put phosphine in here and the reaction would go to the left. So we put in nothing but what we consider products and it shifts to reactants. So but QC will allow us to determine at this stage of the reaction, where are we going, to the left or to the right. So first let's just do it out and then we'll see how we can determine that. Let me get this on here. So QC has the same form as KC. It's just that the concentrations we put in there aren't equilibrium concentrations. They're concentrations at some time during the reaction. And then we compare them to KC. So we have, and there's no, we don't put in the ice table because we're not trying to find equilibrium. So there's no minus X, plus X kind of stuff. We're just going to find the concentrations. Let me see if I can fit everything on here. So for phosphine, it says that we have 7.5 moles of this over a 40 liter container. And I know this is probably, these next two aren't going to be on. I'll shift them up in a second here. Just to do it out long ways so you can see what we're up against. So from the above information, it shows we have 2 moles of P2, 5 moles of H2, 7.5 moles of pH3, and it's in a 40 liter vessel. So we take that data and make sure I got it the right correspondence here, and then we determine our concentrations. 7.5 divided by 40, now we're at 0.188 molar. We have to be in molars before we use our equation. Our QC equation. So this is 0.125 molar. And then 2 divided by 40 is 0.0500 molar. I'm going to double check each of those first before we go on. Yes, 5 divided by 40 looks good. 2 divided by 40. So now we have our concentrations. Now we put them into our expression above. Determine QC and then compare it to KC. Now, if you haven't seen this before, you say, well, how are we comparing them? What are we doing? You'll see in a second. But it's better to get the values in here and have QC set up. And 0.125 cubed. And we end up with 362, according to an earlier calculation. Now, KC is 14.3. When the concentrations are set up so that QC equals 14.3, then we're at equilibrium. But if QC is not equal to 14.3, then we're not at equilibrium. And what does that mean? We have this number that's very large, larger than KC. So these concentrations have to keep shifting until we get to 14.3. That's when the reaction will be done. So if we could follow the concentrations, we could actually see them as they're reacting. We'd see that we have too much here. We don't have enough of these. So this value is going to drop, and these values are going to rise, and both of those things are going to cause this number to drop. So since the product is decreasing, or the product has to decrease to get to 14.3, the reaction has to shift left. So the reaction shifts left. That's good enough for me on the exam. Have to, if the different instructor, then check, do they want you to say reaction shifts from products to reactants? Or do they want you to say that you build up, you decrease products, you increase reactants, something along that line? For me, reaction shifts left tells me enough. So when QC, when we do any of these, when QC is greater than KC, the reaction shifts left. You have too much product, and the only way to get to KC, which is where that number is headed, is to shift left. When QC is less than KC, it means you don't have enough products, so it shifts right to build up product, reduce reactant, and get to KC. And if QC happens to be exactly KC, you were at equilibrium all along. And it was a little trick question. On my exams, if that happened, that would just be by chance. And I would have just picked just the right numbers. But if if QC is even slightly different than KC, you have to go with the higher or lower to determine what's going to happen. So on the exam, that would just be, and it would be very hard to do that too. You can see, even if you're off by just a percent, you can say that it's higher or lower. But if they were exactly the same, then it would be equilibrium. Okay, so here's another one to try. So the concentration of CO, I'm just going to do this first before we do anything else. 15 liters. And then the concentration of CO2 is 0.115 moles over 15 liters. Didn't leave myself a lot of room there. What about the carbon? Well, carbon is a solid, so it's not part of the equilibrium constant. Equilibrium constant expression, so we don't have to worry about it. You might say, well, it's still there. So yeah, but it's a constant itself, that its concentration won't change, so it's already been put into the Kc value. And if that doesn't make sense, as far you're not sure what I mean there, the book has the derivation, and I go over that in class as well. But the big thing is, since it's a solid, it's not part of our Kc expression, and therefore it's not part of our Qc expression. So we don't have to worry about it. And that's why the value wasn't given. Now, I do have to say here, a small amount of carbon, because I have to indicate that the carbon is present. It has to be there for the reaction to go, but I don't say what the moles are because it's unimportant. As long as there's a small amount of carbon, enough to allow the reaction to go, that's the only thing you really have to say. So it has to be present, but we don't worry about its concentration because its concentration doesn't change. And so this comes up to be 0.155 squared, 0.00767, and this is 3.13. And KC is 7.51. QC is less than KC, so the reaction must shifts right. You can see that this ratio is not high enough yet. It has to be equal to 7.51 at the end of the reaction. We're in the middle of the reaction, and this ratio is 3.13. The only way to get to 7.51 is to increase the amount of CO, decrease the amount of CO2, and what that means is the reaction is going to the right, or going forward, going from reactants to products. And I should say, these are long problems. If I get to this point, everything's right, and I make a mistake on this number, please let me know. But also know that, if I put down here 31.3, that's a little calculator error. Trust, if you've gotten all the rest of these numbers and you come up with 3.13, and then you try it again and you keep coming up with the same number, certainly contact me or your instructor. But trust yourself too. That I must have made a mistake. It looks like everything's good here, but don't sit and try desperately to come up with 31.3 when you've done everything the same way I did, and I just wasn't paying attention on that last thing. So I'll take care of it if you let me know. But also, you shouldn't sit. If it's 1 o'clock in the morning when you're doing these, don't sit there for 6 hours typing in the same numbers over and over either. Trust yourself on these things.